My name is Dan Oake and I'm a student at Athabasca University, currently taking the course Computer Science 444, Embedded/Robotic Programming. And if you've been following the videos I've been posting to the course forum so far, you'll know that I'm going through the SparkFun Inventors kit and I'm showing you how I'm completing the projects and the associated coding challenges with the projects. So far in the course forum, I have videos posted showing me completing projects 1 through 4 and all of the circuits and the associated coding challenges for each of the circuits. I also have videos posted showing me completing the coding challenges for Circuit 5A and 5B, the first two circuits of Project 5. In today's video, I'm going to be completing the coding challenge for Circuit 5C, the third and final circuit associated with Project 5, and it also happens to be the final circuit of the SparkFun Inventors kit. So if you followed all the videos I've posted in the course forum and you've been working along, congratulations, you've completed the SparkFun Inventors kit, after this video of course. If you haven't watched those videos, I would highly recommend you watching those before watching today's video, simply for the fact that some of the concepts that I'm going to be discussing today, I'm only going to be touching on the surface because I've already explained them in greater depth in the previous videos. However, if you do feel comfortable watching today's video, and if you do end up having any questions afterwards, just post them on the course forum and I'll be happy to answer. So as I said, in today's video we're going to be showcasing Circuit 5C from the SparkFun Inventors kit. And this focuses on an autonomous robot that can navigate and avoid obstacles. So I'll start with the circuit setup where we have two DC motors controlled via a motor driver. We also have the HC-SR04 ultrasonic distance sensor, which allows the robot to detect obstacles in its path. The robot's behavior is primarily managed in the loop function, where it constantly measures the distance to an obstacle and then reacts accordingly. So if the object is too close, then the robot backs up for a specified time and turns to avoid the obstacle. Otherwise, it drives forward. The setup involves initializing the motor pins, setting the trigger and echo pins for the ultrasonic distance sensor, and beginning serial communication for debugging and monitoring. Now, after we're done with the basic circuit that from the code that's provided by the SparkFun Inventors kit, we're going to transition to my coding challenge, where I've enhanced the original functionality by incorporating multiple control modes. We have an autonomous mode, an infrared remote control mode, and an RF transceiver communication mode. And these three modes will allow for versatile operation. But what are these three modes? Well, autonomous mode is the mode that the robot starts in, where it takes no user input and it just drives and it avoids obstacles by backing up and turning, as I indicated above. And it's done primarily by use of the HC-SR04 ultrasonic distance sensor. In the infrared remote control mode, that's where I'm able to control the direction the robot moves in and the speed at which it moves via commands sent through button presses on a TV remote control. And then finally, in the RF transceiver communication mode, that's where I'll be able to control the robot wirelessly by using a separate laptop that's hooked up to another Arduino microcontroller fitted with a separate NRF24L01 Plus module. So for that type of communication, I'm going to have two separate microcontrollers, each fitted with an RF transceiver module to allow for wireless communication between them. Now, this expanded functionality is demonstrated in Run Autonomous mode, Run IR remote mode, and Run RF transceiver mode functions, as I leverage the IR receiver to toggle between the modes using specific commands, such as switching to autonomous mode when a particular button is pressed. So what does this mean? Well, this means that I'm a really big fan of modular coding. If you've watched my previous videos, you'll know that I like to make a lot of functions, helper and utility functions, and all kinds of functions, just because I like making my code modular. It's breaks down a large problem into smaller pieces, and it just makes it easier to maintain the code. And it also allows my code to read kind of like pseudocode. So if I'm looking at my setup and loop, it's very obvious what's happening as I read through it. So I'm a big fan of that. If you've watched my previous videos, you'll know that. And how do I switch between these modes? Well, as it says, I leverage the IR receiver, which is hooked up on my circuit, which I'll show afterwards. And just using specific buttons, I'm able to toggle between the modes. I've also added code to manage speed adjustments and LED indicators for each mode, providing visual feedback on the robot's current internal state. So for example, when it's in autonomous mode, the green LED is lit up. When it's in IR remote control mode, a red LED is lit up, And finally, when it's in RF transceiver mode, a blue LED is lit up. And these are 3 discrete LEDs. I have 3 separate LEDs, a red, a green, and a blue. If you've watched my previous videos, you'll know that I'm a big fan of RGB LEDs, which are when you have the 3 LEDs housed in a single LED. But that's not what is happening here. So they are 3 discrete LEDs. As I navigate through the code, I'll explain the highlights and the key logic elements that I've used, such as measuring distance from the ultrasonic distance sensor, processing IR commands, and executing motor control functions based on received signals. I'll also run a live demonstration showcasing the robot autonomously navigating around obstacles while also responding to IR commands via the remote control, and show how I'm able to control the robot wirelessly via communication with the radio frequency transceiver module. This project exemplifies not only fundamental robotic principles, but also offers insights into effective programming and code organization for complex projects. So join me as I explore the capabilities of this autonomous robot, and as always, I encourage all Comp44 students to post any questions you have on the course forum, and I'll be happy to respond. So if you have watched the previous videos I posted, you'll know that I typically start by going through the SparkFun Inventor's Kit Guide and just reading it through so we have a general idea of what the basic project is. So I typically don't read the guide in its entirety, but rather I just kind of, indicate some of the highlights. And that's what I'm going to do today as well. So today's circuit, Circuit 5C, is all about autonomous robots. So we want to unplug your robot from the computer and just let it navigate the world on its own. And that's what we're going to do. The robot is going to sense an object using the distance sensor, and then it will back up and change course. So if you watched my previous video where I went over the coding challenge for Circuit 5B, we already did unplug our robot in one sense. The original circuit called for you to send commands via the serial monitor to the robot that it would respond to, going forward, backward, right, left, that sort of thing. But the idea was that you were tethered via a long USB cable hooked into the microcontroller, the SparkFun Redboard, and your computer. However, for the coding challenge, I employed the use of the NRF 24L01 transceiver modules, the RF transceiver modules, to untether myself in the last circuit as well and communicate wirelessly, just like we're doing again in this one. So we were already unplugged, but now the robot's going to be able to navigate the world on its own. So the components that we're using are largely the same that we've used in the past couple circuits. The motor driver, we're still using the switch, and 2 gear motors. I actually have taken the switch out just because I ran out of room because I've got so much other things going on. I just didn't have any availability for it. And we're also going to be using the distance sensor. We've used that previously, I believe, in Project 3, but this is the first time we're incorporating it now with our motors. We'll also be discussing some new concepts today, mainly that of autonomous vehicles. So where we're going to use the simple sensor, the ultrasonic sensor, to avoid obstacles. So the Mars rover, other autonomous cars, so self-driving cars, and bots of all kinds that you see in robotics competitions, all use this kind of similar concept to navigate and avoid obstacles. One thing to keep in mind when we are using the ultrasonic distance sensor is we want to keep the distance sensor clear of any wires from your circuit. So again, the whole point of it is it measures the distance to an obstacle, and reports that back. And the way our code's set up, if there's an obstacle right in front, we're going to back up and turn. Well, if the obstacle is the wire that's right in front, we're going to constantly be in that loop. So let's just make sure our field of view is clear in front of the ultrasonic distance sensor. The next bit of text just shows how to attach your battery pack underneath your chassis of your robot. And then the hookup guide. So SparkFun is really good with their hookup guides. They provide really nice schematics that are easy to follow. I'll just briefly touch on this. To be honest, there's not much that has changed if you watch my previous videos. The only addition to this circuit from Circuit 5B is this ultrasonic distance sensor. Everything else is the same in 5B. And the only thing that changed in 5B from 5A was we added a second motor. So I've already went over this same circuit schematic a few times, but I'll briefly mention it again here. So the motor driver, which is what feeds the power to the motors, because motors draw a lot of current and therefore aren't effectively controlled or powered via a microcontroller itself. So instead, we typically control them with a motor driver. In this case, This is the TB6612 FNG motor driver, a very efficient motor driver. There's just lots of motor drivers out there though. But the motor driver itself gets its power via 5 volts from the microcontroller. You can see the VCC and ground are hooked up to the power rails of the breadboard, which are hooked up to these power rails. They're tethered together, and ultimately are getting their power from the 5 volts and ground of the microcontroller. However, the motors, which get their power via channel A's input or output 1 and 2, and motor 2 gets its power output from channel B's output 1 and 2, which ultimately go to the 2 motors here. Those are powered via the power that's coming in through the VM pin, VM for the voltage to the motor. That's getting its power not from the 5 volts of the microcontroller, but rather from the V-in pin, the voltage in pin of the microcontroller. And where does that get its power, you ask? Well, that comes in through anything that's hooked in through the barrel jack here. So it accepts anything with a voltage from 7 to 15 volts, and typically that would be where your battery pack is hooked up. So for example, I'm using a battery pack that holds 6 1.5 volt batteries for a total of 9 volts, which as you can see is in the range of 7 to 15. You can also just use you don't quite need that much, just 6 volts would be fine to power these motors. But so that's really the change here. For motor 1, channel A, we have our PWM pin A and our 2 input pins. They're hooked in here, and the channel B pins, so the second motor, are connected here. On each of that, the inputs A1 and so input 1 and 2 are your directional pins for motor 1. Similarly, B1 and B2 are your directional pins, and each motor has a PWM pin, which do have to be hooked up to PWM pins, pulse width modulation pins. And the pink is PWM pin A on pin 11, and the green wire is PWM pin B on pin 10. And you can tell they're pulse width modulation pins because of the little tilde symbol beside the number. And then finally we just have the standby connected to our positive 5 volt rail. So that's the schematic in a nutshell. Again, we've discussed that in greater detail in the previous circuits. So what should you see when you're done the circuit? Not my coding challenge, but when you're done the basic circuit 5A, or 5C rather. Well, when the switch is turned off, the robot will sit still. Now I've technically removed the switch, as I said. I had the switch in my 5B circuit, but I just ran out of room in this one, so I've actually removed it. So my switch will be physically plugging in and unplugging the battery pack from the barrel jack. But when my battery pack is unhooked, is not plugged in, my robot will sit still. Yours will sit still when the switch is off, if you're just following the regular circuit. When the switch is turned on, the robot will drive itself. It'll just drive forward until it senses an object. When it senses an object, it will reverse and then turn to avoid the obstacle. That's what this robot does. It's not meant to have any user input. It's just going to drive autonomously. Now, that's what mine's doing too, until I decide to override it and control it via remote control and wirelessly via the RF transceiver modules. But the original circuit, that's the overview. It starts sensing the distance right away. If there's no obstacle, it just keeps driving forward. As soon as an obstacle is detected, it stops, backs up, and turns right. If no obstacle is detected again, it starts driving forward again. That's pretty much its pattern. It's always driving forward unless there's an obstacle in its way, where it'll stop, reverse, and turn right. These are the standard warnings we've had before when we use the ultrasonic distance sensors. If you're near an HVAC system, your air conditioner or something like that, they've been known to interfere with the performance of the sensor. So if you're experiencing sporadic behavior from your circuit, check your surroundings. If you're right next to a register or an HVAC system, that might be some of your issues. So, relocate. The coding challenge. The coding challenges for this circuit, I didn't find that challenging or that interesting. For example, one of the coding challenges, as you can see here, is change the distance at which your robot reacts. Well, that's really just, the distance my robot reacts is just a constant that I've created in my program. So it's really just changing that number. That takes, seconds to do. And now, the distance is different. Not really a coding challenge, in my opinion. Nothing really interesting there anyway. So then the second coding challenge is to change the behavior of the robot when it senses an obstacle. So that's a little more interesting. However, I opted not really to do that because really all I wanted to do is do what it was originally going to. Stop, reverse, and turn right and get out of there and try to find a new path it can go. I mean, you could change that instead of turning right, you could turn left, that sort of thing. You could make it back up further, or, you know, not back up at all until it gets closer, so allowing you to get closer to the obstacle before it turns around. There's little things you could do with that, but again, there wouldn't be that much changing the code to do. It would be simple changes. So for my coding challenge, I just went off script here, and I decided just to add wireless capability so I could control it wirelessly when I didn't want to drive it autonomously, and I wanted to add remote control as well via TV remote, specifically my LG TV remote. And then ultimately we'll run into some troubleshooting issues, but we'll go over that after we've talked a little bit more about the coding challenge specifically. So I want to just discuss a couple key points about the components that we're going to use that I've picked up by one in the SparkFun Inventor's kit guide, but I've also read online and watching different tutorials. And these points I picked up from watching videos online from DroneBot workshops. So if you haven't watched DroneBot workshops before, it's an amazing YouTube channel. The guy is like really thorough and detailed and does a really good job explaining Arduino and programming and all of the different components, and he makes some really cool things. So I've watched videos on each of the components in today's circuit, and these are just a couple highlights from those videos, and I would highly suggest watching them. I'll put links to them in the YouTube description. But in general, if you're at this point, you may know these things about these components, so I'll just briefly talk about them. The HC-SR04 ultrasonic distance sensor, it's an ultrasonic distance sensor for measurement applications. It measures distances typically from about 2 centimeters to 400 centimeters, theoretically, using sound pulses. It has 2 pins that get hooked up to the microcontroller. The trigger pin sends out pulses, so it sends out a 10 microsecond pulse. And the echo pin is for receiving reflected signal. So it receives as input a high-level signal. And the duration of the signal that it receives is proportional to the distance the object is in front of the sensor. Also, care should be taken when using ultrasonic distance sensors. So I mentioned that you might get sporadic behavior in your circuit if you're near an HVAC system, but that really doesn't do anything besides irritating you that you have to keep recoding things or wonder why your circuit's not working. But you should also take care around animals, because animals are highly sensitive to these sort of things because they have, due to their high frequency sounds. So the ultrasonic sensor, again, is sending out high frequency sound waves, and we know that animals are more sensitive to that. And, if they are around when you're doing all this stuff, it can cause some issues. So just take care when doing that. Then we have the IR receiver key points. So his video on the IR receiver basically goes over decoding complex remote signals. He goes in a lot of detail. It's really informative. He explains basic IR functioning, the NEC protocol, which is the most common standard for various remotes, including the remote I'm using, I believe. He also talks about IR receiver modules and emitters. So right now I'm using an IR receiver module in my circuit because I'm receiving commands sent from the remote control. But my TV remote controller has an IR emitter. So when you look at the top of your remote control, there's always a little emitter bulb on there. And normally in my videos I show the circuit as I'm kind of talking through. However, I'm having some difficulties with my webcam application, so I'm going to show those all after the fact. So do stick along. There will be a live demo as usual. I just need to sort out some technical difficulties. And the IR receiver video also talks about the use of libraries, which make the code a lot easier to use. And that's always the case pretty much when someone else has done the work to put up a good library. The video for the NRF24L01 Plus transceiver module key points are basically it allows for wireless communication between Arduino boards. It works on your standard 2.4 gigahertz band. The typical range is about 1,000 meters for the external antenna versions and about 100 meters for your built-in antenna versions. So in my circuit today, I'm using both the external and the internal versions. The external version is hooked up to my circuit with my remote control car, and the internal version is what I have hooked up to my second Arduino that will be attached to the computer, where I'll be sending the serial communication from. So in that case, you'd kind of default to the lower range, obviously the 100 range, but none of it matters for today because all my demos are going to be within my living room. So, I'm 30 feet apart at most if I'm wall to wall. The video also discusses the SPI pins and their use. So the RF transceiver module does work using the serial peripheral interface protocol. The video also goes into talking about bidirectional communication. That's not what we're using today. Ours is kind of unidirectional, but it discusses all those different concepts and talks about using bidirectional communication using sensors and actuators. Talks about the RF24 library. Again, libraries in most sensor modules. There's going to be someone who did up a nice library for it, and they're always going to be to your benefit to use. Just makes the coding so much easier. Another thing to keep in mind when using these modules is proper power supply and grounding are critical for reliability. So again, they're affected by noise and other things a lot. In fact, once I get my camera working, I'll show you my NRF transceiver modules I have now. I actually have a capacitor soldered across the VCC and ground, so across the power, as per recommendations from the interwebs. So just to help with the power issues, and that is something that it's a known bug sort of thing with these modules, but unfortunately they usually don't come with the capacitor pre-soldered. So just soldering something like a 2.2 microfarad capacitor across the power rails works wonders. By the way, because some of these things might sound Greek to you if you're not that familiar, I do have videos showing me go through these sensors in greater detail. I have videos on the ultrasonic distance sensor on the course form, as well as the IR receiver, and quite a few videos on the wireless transceiver modules. I think I have at least 4 videos that talk about this in great detail, so feel free to look those. I'll try to link them in the description as well. And then driving DC motors with motor drivers. So DC motor drivers, or DC motors, rotate. That's what they do. And changing the polarity just reverses the direction. That's different than other things that are polarized. So LEDs are polarized, and if you put them backwards, they either won't work or likely it'll damage the LED. It'll destroy it. So that's not the case with DC motors. When you just reverse the polarity, you simply reverse the direction the motor spins in. And H-bridges control motor spin and direction using 4 switches. They take advantage of this polarity issue where when you reverse the polarity, you switch the direction. So an H-bridge controls the speed and direction using 4 switches. And the H-bridge is kind of the internal mechanism behind our motor drivers. We could create an H-bridge just using discrete components, but we have no need to. These motor drivers are fairly ubiquitous throughout Amazon and AliExpress and all that. You can get them, and they're really efficient, and they have that H-bridge already incorporated in them. So there's lots of common motor drivers. One of the common ones that you'll find in a lot of kits is the L298N motor driver, and I've used that in some of my previous videos as well, just because I got it in some of the kits I bought. It is very common. There's a lot of tutorials about it online because it is such a common motor driver. However, it's not as efficient as the one we have in our kits. The TB6612F&G is just a lot better. Again, when I have my camera up, I'll be able to show you that the motor driver that we all have in our kits doesn't have a heatsink. Okay, whereas the L298N has a huge heatsink, indicating it's not quite as efficient. You're wasting a lot of power. The speed control, the way the motor drivers works, is it uses PWM, pulse width modulation, to control the speed at which the motors spin. And then just regular digital pins are used to control the direction. And that's pretty much it. I have some other things. Might as well just mention this. So this is, again, what we're going to be going. We're going to be diving right in here in a minute. I know this has been a long intro, but I'm just trying to get you guys prepared for fully what we're doing and to understand the concepts before we start looking at the code. So again, in today's SparkFun Inventor's Kit 5C Coding Challenge receiver program, it effectively combines autonomous navigation, IR remote control, and RF communication for an Arduino-based robotic system, allowing it to operate in 3 distinct modes. In autonomous mode, the robot utilizes an ultrasonic sensor to detect obstacles and maneuvers by reversing or turning to avoid those obstacles. While in the IR remote mode, it enables users to control the robot via an IR remote, so my TV remote, allowing for directional movement and speed adjustments. The RF transceiver mode facilitates communication between two NRF24L01 Plus modules, enabling wireless command reception, which allows for controlling the robot's movements and speed instructions sent from the serial monitor of a separate computer that's connected to a separate Arduino microcontroller and NRF24L01 Plus module. So, comprised of adjustable motor speeds and LED indicators to denote operational mode, the program is designed for flexibility and ease of integration, making it suitable for various applications in robotics and remote control tasks. Various motor functions are implemented for driving forward, backward, and turning, along with support for speed increments and decrements, ensuring that the robot can respond dynamically to both automated and user-directed commands, while maintaining a stable performance. Additionally, the code includes measures to prevent redundant actions through the use of state tracking, debouncing techniques for the IR receiver, and a well-structured command parsing system, making the robot highly responsive and reliable in diverse environments. So this is a big part of my code, is the code includes measures to prevent redundant actions through the use of state tracking. So I've got a lot of state tracking, a lot of Boolean flags that allow me to not repeat the same code over and over if I don't need to. So that's what, and I use a lot of debouncing. I'll talk about my coding choices after. You can see it peeking through there, after we actually get looking at the code. So for today's video, I'm going to try to do it a little different. I've got 2 pieces of code here. Again, because of the RF transceiver mode, where I'm able to control the robot wirelessly via a laptop hooked up to another microcontroller and NRF24L01 module, I have to have a receiver code, a transmitter code, and a receiver code. So the transmitter code, as the name would imply, sends the commands from the laptop and the Arduino that's hooked up to the laptop to the receiver code, which is the microcontroller attached to the vehicle. And so we do need these 2 separate codes. However, the majority of the code and of what's of interest today is going to be in the receiver code. In my previous videos where I've already discussed the RF transceiver modules, I've already went over both the receiver and transceiver code in detail. And so, although my transceiver code has a lot of other stuff in it because of today's coding challenge, the receiver code is very similar. You can see how short it is too. So there's not much to it. So we'll talk about that, but we're going to start with the receiver code. However, I am doing things a little different. Instead of going through the code in the IDEs like I've typically done, you'll notice whenever I hover over something in the IDE, it automatically pops up sometimes. It's not doing it right now. But, well, this is not proving my point at all. But typically when you hover over, you get the IDE automatically popping things up in order to, and it's not doing it all right now. But typically something would pop up and give you a little prompt letting you know, the CE pin, what it is. And so to avoid that, I've copied both codes into a PDF, and I'm just going to go through it on the PDF. So the code in the PDF is identical to the code in the Arduino IDEs, but the big difference is that I won't have any pop-ups, and that way it won't cause any distraction. As a side note here, I have color-coded some of the code just to help us follow it easier. Any utility/helper functions, or code for that matter, are just highlighted in gray. Anything associated with the motors is highlighted in blue. The driving modes highlighted in purple. The ultrasonic distance sensor code in pink. The NRF24L01 Plus RF transceivers in green, and the IR remote receiver in red. So without further ado, let's just start reading this code. So again, this is the receiver code, which is the bread and butter of this project. as anyone who's followed my previous videos knows, I'm a big advocate of Doxygen style comments, and that's all this is. If you're not familiar with these little tags, by adding extra asterisks to a multi-line comment, I suddenly make this a Doxygen style comment, and then I can add these little tags like @file, @brief, @details. Typically, I notice I've neglected here, but I typically have an @author tag and @date, which lets me put my name and the date I produced the code in. Lots of other things you can do in functions and stuff. I'm a big advocate of it. It basically allows you to take your code and run it through an external program, in this case Doxygen, and it'll automatically generate some really professional looking HTML documentation for you from your code. Akin to that you'd find if you went to like a CPP reference website or an Arduino function reference source online, you would get some sort of nice documentation done up. Well, you can create your own with this external program and just modifying the way you code or the way you comment a little bit. Sorry, I meant to read this. So what does this program do? Well, let's just read. This program implements 3 modes for controlling an Arduino-based system. Number 1, autonomous mode. So obstacle avoidance. It operates without user input. Number 2, IR remote mode, controlled via an IR remote. And number 3, RF transceiver mode, which communicates via the NRF24L01 Plus modules. So, and the active mode is toggled using specific IR commands, i.e. via the TV remote control. So, the motors, here's the mode. This is all code in blue that's associated with the motors. So as usual, we've got a lot of constants for just various values. So my default speed, 125. Max speed is 250. Min speed is 100. Speed increment, because I'm going to be able to increment the speed via the remote control. I have that set at 25, so I increase in increments of 25 or decrease in increments of 25. Right away, I want to set my motor speed to the default speed, 125. And my current speed is 0. This tracks the current speed of your car. So why do I have all these constants? Do I need them? Well, not typically. I could just put these numbers into the code wherever I'm using them. Like for example, I created default speed here and I immediately use it here. I also use it throughout the code, but here's a good example. I use it here. Could I have not just put 125 here? Absolutely. I love using constants because they make the code more explicit. Like later on in the code, when I'm going to say something like, when I'm checking some value and making sure my current speed is less than the max speed, I'm going to be able to say current speed less than max speed. That's going to be very clear, almost English-like, into what it's explaining to be done. That wasn't English-like, the way I just stumbled over my words there. But if I just had, if the current speed is below 255, for a lot of people who code, that makes sense. 255 is probably the max speed, PWM, but it's just not as intuitive. Why 255? Oh, yeah, because that's the maximum PWM I can give. No, it's better to be explicit. So I'm a big advocate of using constants. And as such, here's constants for all of the motor inputs. Now, a lot of this code is from the SparkFun Inventors Kit website for the original circuit for 5C. So some of this I haven't modified. So throughout this code, you'll see some that you just might recognize from the actual SparkFun code master folder. And then other times you'll see that I've adapted it or I've got a lot of my own code in here. But in either case, this is from the SparkFun website. It just shows they've just created constants for the 2 inputs for motor A and the PWM as well. So the two input pins allow for directional control, so they control the direction that the motor spins in, and the PWM pin controls the speed. And similarly for the other motor, we have the directional pins and the PWM pin. So again, the PWM pins do need to be hooked up to PWM digital pins, and they both are. Then we've got this constant drive time, which is just a constant int assigned to 20, and this is the number of milliseconds that it takes the robot to drive 1 inch. At least this is what it took SparkFun, the people who made the code, to drive their robot 1 inch on their floor with their friction. And the idea here is that now if I tell my robot to drive 25 units, it drives about 25 inches, 1 unit per inch sort of thing. You might have to adjust this number to actually match these measurements on your own floor with your own motors, but that's not really important for this video, so we're going to move on. And the turn time is very similar. It's the number of milliseconds it takes to turn the robot about 1 degree. So that way if you tell the robot to turn 90 units, it should theoretically turn about 90 degrees. Again, this comment just says you might have to adjust these numbers on your own. And then we've got a couple of string variables representing the direction the motor, the robot will drive in, and the distance that it will drive in. And now we've got our driving mode code. So again, in purple, just to indicate that we're in driving mode code. So we start off by creating an enum, which I went over before. If you're not familiar with enums, it's essentially kind of like a class, just made up of integer constants. So under the hood, autonomous is the integer 0, IR remote is 1, and RF transceiver is 2. It just gives constant names to those. Kind of the same reason I just said why I love constants. Well, enums are essentially a class of constants. And if I can show you here in the IDE, so again, I'm not sure why this is not defaulting. Let me just reopen this. So typically, the whole reason that I did copy the code to a PDF was not just to make it all colorful and pink. It was because of the fact that under normal circumstances, this code, it's under normal circumstances, the code as you hover over it highlights and essentially, gives you extra information. So I'm not sure why it's not doing it right now. If it was, I would hover over this and you would see that this is a number under the... Oh, you know what? I just realized it's because I don't have any board hooked up. That's why. So if I hooked up a board, it may actually, in fact, show me what I need. I'm not sure if that's the case, but let's just try. These videos aren't meant to be a perfect polished product. They're more or less meant to help us learn, discover, all that sort of thing. So if I hook this up, the board is now hooked up. No board is selected. Pin 9. Let's hook up the Uno. Okay, so I didn't really need to re-upload the code. There you go. So now it's showing up. So this is what I was talking about before. This is why I created the PDF. Normally, every time I'm hovering over something to talk about it, I'd be talking about the thing and this little pop-up is constantly showing up, which is quite annoying. And it's just funny that it didn't show up this time because I didn't have the boards hooked up. But as you can see, under the hood, autonomous, this constant, is really just the value 0. IR remote is the value 1, and RF transceiver is the value 2. So we'll unhook that. So we might not get any more pop-ups because I just unhook things, but yeah, it seems to still be working. So yeah, under the hood, these constants are just integer values. They're integral values. We also set up the current mode as autonomous. So mode is, again, of type this enum class. And the previous mode is -1. You'll see that there is no -1, this 0, 1, and 2. So -1 just indicates a mode that we haven't already had and we won't ever have again. This is just done so that I can, when I am checking for a state change, the first time it works. That's why I have this set up as -1 from the start. Then I also have constants showing for the RGB LEDs, the different pins the RGB LEDs are all on. You can see red, green, and blue LED are on pin A2, A3, and A4 respectively. And you're probably wondering, why am I having them on analog pins? Aren't LEDs always set up as outputs, and therefore analog pins are inputs by default? Correct? Well, you are correct. Analog pins are by default input pins. However, analog pins are really just, they're under the hood, they're just general purpose input-output pins like all the other digital pins. They've just been given us some extra functionality associated with the analog input. However, we can choose to use the pins as digital pins if we want and if we need. And in my case, I needed it because, again, if I had access to my camera like I normally do, I would just show you my circuit right quick and show you that all of my digital pins, with the exception of 0 and 1, which are your receive and transmit pins, are used up because of my NRF 24L01 module, my motor control pins, and that sort of thing. So I've used up all of my digital pins. So I've had to hijack the analog pins for my LEDs as well as for my trigger and echo pin associated with my ultrasonic distance sensor right here. But as long as you just configure them in your code as digital pins, they work the same. So I'm not using the analog capability of these pins, I'm just using them as digital pins. So that was a long explanation, but that's why I have all these analog pins here. I've also got a bunch of Boolean flags for the red LED state, green LED state, and blue LED state. And again, that's just used for some efficiency, as well as allowing me to toggle the LEDs on and off fairly easily. Same with this red toggle Boolean flag, which is going to be used in my RF mode, and the last LED state. Moving on to the ultrasonic code here in pink. Again, I've got my constants for my trigger pin and my echo pin. And again, these are normally just plugged on any digital pins. They don't need to be analog, nor are they even supposed to be analog. They're just meant to be hooked up to digital pins, and neither of them need to be PWM either. So they're just regular digital pins normally. So don't be confused that I'm hooking them up to analog pins here. And the reason that they don't need to be PWM pins or anything is because the trigger pin is simply outputting a pulse for 10 microseconds, so it's an output pin, and the echo pin is an input pin that's receiving a high signal for a certain amount of time, and the duration of the signal that it receives is proportional to the distance an object is in front of the sensor. But so both of them just need to be regular digital pins. The obstacle threshold I have set at 25 centimeters. And then moving on to the RF transceiver, or the radio code, as usual we include the RF24 library, and then we've got a couple constants for the pins associated with the transceiver, namely the chip enable pin and the chip select not pin on 4 and 3. Now there are a lot more wires that are hooked up to pins on our Arduino associated with the RF transceiver. It's just the only two that you have to specify are the CE pin and the CSN pin, because the other pins occupy pins 11, 12, and 13 of the microcontroller, because they're the SPI pins, the serial peripheral interface pins, and those kind of really have to be there. You don't necessarily have to, but if you're using the library and you want, your life not to suck, and the code to actually be, easy enough to do, you want to use those SPI pins. Also, another important note is make sure you're powering, if you are using this transceiver module, make sure you're powering it with the 3.3 volts from the microcontroller and not the 5 volts, otherwise you might ruin your board. I won't talk too much about the modules themselves because I do have other videos on these modules specifically. In fact, I have at least 4 videos really just going through these NRF 24L01 plus modules, not even doing coding challenges associated with the SparkFun Inventor's Kit Guide, just separate coding examples. And then plus I have used these before in my other projects. So there's lots of information I have on my videos about these, so I won't go into too much details. But to say that you do need to create a instance of the RF24 class, and by convention you typically just name it radio, and we use a parameterized constructor passing in the CE pin and the CSN pin to create that object for wireless communication. And then we need an address, and it's typically just a C-style string, so a one-dimensional array of type character. And this address has to match the address of the transmitter code, so the transceiver that is set up to transmit to the receiver here. We have our IR receiver code, which we again include the libraries for ease of use. We have a constant for the IR pin, so it's set on pin 2. That's the only one you have to specify. We've got a blue LED toggle, Boolean flag, just like we had a red LED toggle up with the other code. And all this code here is for debounce, our debounce code. So I'm using time functionality. If you watch my previous videos, you'll know I'm a big advocate of not using blocking code, i.e. not using the delay function, which just halts the execution of the Arduino and doesn't allow for other things to be happening at the same time. I don't like using blocking code. Instead, I prefer to use time functionality and non-blocking code such as this. So I won't go into too much details because I've talked about it a lot, but suffice to say it is the preferred method for debounce. Whether that's button debounce, which is what I'm using for the IR receiver. When I press buttons on the remote control, I want nice debounce. Now I'm using an LG TV remote control, so it does have hardware debounce, I think, built into the buttons. But if you were using the little remote controls that come with the Arduino kits you can buy online, like from Elegoo and stuff, you definitely, they don't have the same hardware debounce. They're not great remotes, so you'll definitely want to have some debounce logic. You might be noticing that I'm, instead of using int or something, occasionally throughout my code I'll use stuff like uint32_t or uint16_t or 8_t. This is just an efficient way to tell the compiler and the program what type of integer sorted to use. So I could have used int. I could just simply put int here and that would have been fine. By using this, it's more efficient. It allows for cross compatibility. When I run this code on all kinds of different computers, depending on the size that it would allocate to an int, I'm saying no matter what, allocate at least this much size, so 32 bits or 4 bytes to this command, to this variable rather. So that's what it's doing. And if it has to allocate more because for whatever reason the computer I'm using uses 64 bits regardless, then it would assure that you use the minimum amount required. So this is just an efficiency thing. I explain this in greater detail in other videos, but you could have just used int here if you wanted. And then I've got a couple command definitions, so a couple constants, again using uint16. So I don't need quite as much room, I guess, for these ones, I've decided, because I'm using hex values. Yeah, these are just a couple constants. So I've got command autonomous, literally gets assigned this hex value B0, and the hex value 44 gets assigned to command IR remote, and so forth. Hex value 72 gets assigned to this. Their hex values, in case you're not familiar, when you have a 0x in front of a value, that indicates this is a hex value. So this is fairly easy to tell it's a hex value because it's got a letter B in it and a 0, but there'd be no way to discern this being a hex value or this being a hex value because it looks just like a decimal value if you didn't have the 0x. So this lets you know that this is not the decimal value 44, this is the hex value 44, which means it's a higher decimal value, somewhere maybe around 100 or so, or in the high 90s. So yeah, I'm basically just creating, I could just use these in my code. Again, I'm just creating these for the fact that in my code somewhere, it'll be more, when I say, hey, if something equals command autonomous, it'll be pretty obvious what I want to happen. Then I've got a bunch of function prototypes for all my different functions. I've got utility helper functions. I've got all the functions associated with motors. I've got all the functions associated with the driving mode functions. I got the measure distance function associated with my ultrasonic distance sensor. I've got my functions for my RF transceiver and my IR remote functions. So you can see there's a lot of functions there. And I've talked about function prototypes before. If you're not familiar, they're basically a way to tell the compiler that, hey, I've got a function that I'm going to define somewhere in the code called initialize pins. I'm not defining it here, I'm just declaring it, hence I've just got a semicolon and not a body of a function. But I'm just declaring it here, but I'm promising you that I've got it defined somewhere else. So if you run into this function in setup or loop and you're confused because you're like, whoa, I haven't seen that function defined, it's telling the compiler just to chill out and trust it that that function is defined somewhere. That's the non-technical way to talk about it, but that's essentially what's happening. It's kind of like an IOU, a function. So don't worry about it. And you only have to do this if you don't define the functions above when they're used. So for example, in my code, I typically like to have my setup and my loop as the first two functions, so I can right away see what my code's doing. And then I like to define all my other functions, but because I'm defining them after I'm going to use them, because for example here, I'm using the initialize pins function, but I haven't defined it yet, I have to tell the compiler, hey, this function exists and it's defined somewhere, and I do that via these function prototypes, which basically just means putting the signature of the function with the matching return type and parameters, if there are any, and then just terminating with a semicolon. So again, if you have questions on that, feel free to watch some of my previous videos where I talk about that in more detail, or post a comment on the course forum and I'll be happy to get back to you. So the setup function, fairly simple. I'm calling the initialize pins function. It's just initializing all of my pins. And then I'm stopping the motors. I'm just making sure the motors are stopped initially. That's just a safety thing. Setting up serial communication. I'm using a higher baud rate than I've used a lot of times. I often stick with the 9600. I'm using a little faster baud rate just because I'm communicating via the transceiver modules. And this is another common baud rate, the 115,200 is a lot faster than 9600, obviously, but it's also not too fast that it causes a bunch of problems, because typically the faster you make your baud rate, you can miss some communication, and there can there can just be some skips and stuff. So this is kind of that best value where it's really fast, but not so fast as that I'm dropping a lot of comms. So but this doesn't need to be this. You could make this 9600, that's fine. And then basically until I set up my serial monitor, so while it's not set up, I'm just going to wait for it to set up because I need my serial communication set up before I move on. Once I do move on, I'm going to set up my IR communication, so for my remote control, by calling the IR.begin function. Remember, a lot of these library functions use .begin, just like serial, the radio function, they all use the begin function, a lot of them. And I just need to pass in the IR pin and enable LED feedback. This just means that when there's communication, the onboard LED on pin 13 would flash. I'm not really concerned with that, but that's just an option. You can set it up. You could disable this as well if you wanted. And then I'm just printing out to the console, hey, IR receiver initialized successfully. After I set up my serial communication, my serial monitor, and then my IR communication, I'm going to set up the radio, my RF transceiver. So I'm going to call the init radio function, passing in RX. And this is a user-defined function that I've created, but very similar functions can be found on a lot of tutorials online. It's a fairly common idiom that people use. So I'm passing in RX, which basically says I want to set up this radio in receive mode. And this is going to return a Boolean. True if it's successfully initialized radio, false otherwise. So if it returns false, well, not false, indicated by this Boolean not operator. Not false will be true, so if I didn't initialize the radio, I'm just going to stick myself in a forever loop by going while one, semicolon. This just will halt the program. Basically, I halt the program if the radio fails to initialize, because I can't go forward because one of my modes requires this radio. And then I'm just going to flash the LEDs on setup. That's just a visual cue that everything's working. And then I'm just going to chill out for 5 seconds. Because you know what? I've done a lot of work so far, setting up my serial comms, my IR, and my radio. In the loop, this is the entire loop, so there's not much happening there. That's why I like modular code and setting up my functions so much, because you can get it to that you can have this really short little loop that does everything I need, and it's pretty self-explanatory. If this case, it just goes if the current mode is not equal to the previous mode, meaning if there was a state change in my modes, if I change my modes, then one, I'm just going to set the previous mode to current mode, but I'm going to stop the motors. So basically, if I'm in autonomous mode, and then I suddenly press a button to enter remote control mode, I want the robot to stop for a second. I don't want it to keep driving into a wall while I'm figuring out what button to press to control the robot. So I want the robot to stop. Similarly, if I was in autonomous driving mode, and then I switched into RF transceiver mode where I control the robot wirelessly via another computer, I, again, want the robot to stop for a second and not just ram into a wall. So this is just a safety precaution, really, to stop the robot when I switch modes. Now, I could have put this in a function just called, stop motor when switching modes, and then put this code in a helper utility function. You can do that if you want, break down the code even further so that it reads even more like pseudocode, but this to me seemed pretty self-explanatory, so I didn't want to just make another function for it, but you could. Similarly, you could put this code in a function. What this does is this simply says it's constantly checking to see if you've received a command from the remote control. So IR receiver, if IR receiver.decode, hey, check if an IR receiver has received a signal. Okay, this is kind of like akin to if serial.available, checking if there's something available in the serial monitor. So if there is something, a signal that was sent, then I'm going to handle it, calling the handle IR command function. And it takes in this weird syntax thing, but this is all in the documentation of how to work with IR remotes. IR receiver.decoded IR data.command. This last part's important. .command. If you don't have that, you'll get this weird sort of value. Still usable, it's just weird. But by doing .command, it gives you that nice hexadecimal value that we seen before, where I had like 0x44 or 0xb0 or 0x72. You'll get a hex value by using the command. So this function simply processes the button that I pressed, and then at the end, you always have to tell the IR receiver to resume. Hey, get ready to read another IR signal in case it gets sent. So again, I could have put this in a function just called listen for IR remote control signal or listen for IR remote, and then again, it would read even more like pseudocode, but I opted just to leave this here like this and not make those two helper functions. But you could, if you wanted the loop to really be like 4 lines or something, you could feel free. The heart and soul of the loop function is right here. I'm using a switch statement to decide what to do, what mode I'm going to be in based on whatever the current mode is. So remember, the current mode is going to get set by this handle IR command. So we're not seeing anything happen. It's not returning anything. It's just setting the current mode, which is a global variable, in this command. And then so if the case is autonomous, so if the mode is autonomous, we're going to run the autonomous mode function. If the mode is IR remote, we're going to run the applicable function, and same if it's RF transceiver. Remember, these are constants associated with my enum class that I've created. And then finally, we're going to use that same current mode. So whatever the current mode is here, it's still going to be the same mode here. I'm going to use that to control the LED. So I'm calling a function passing in the current mode, and it's going to light up the applicable LED. So if I'm in autonomous mode, I'm going to have a green LED. IR mode, I'm going to have a red LED, and RF transceiver mode, I'm going to have a blue LED. I know it's a little confusing right here with the colors, but that's the case. So now let's get into the functions. So these are some helper utility functions I have. So initialize pins, we've seen this function at the start of setup. It simply calls the pin mode on all my LEDs, send them all up as outputs. On the ultrasonic distance sensor pins, i.e. the trigger pin and the echo pin. Trigger pin is an output pin, because remember, it's sending a 10 microsecond pulse out. And then the echo pin is an input pin, because it's going to receive in that high signal, representing the distance of the obstacle. And then we set up all of our motor pins, so for the first motor and the second motor. And then we have this other helper function, just flash LEDs on setup. I mean, this is really just for my purposes, just let me know a visual cue, hey, the setup went well. If I didn't have it hooked up to the serial monitor, which would also tell me it went well. But it basically, it just turns on the red LED for, a fifth of a second, the green LED, and then the blue LED. So really quickly, it just goes green, red, green, blue, and indicates success. Again, if you have this hooked up to a computer, you'll get the indication of success through the serial monitor and the lights. But if you're not hooked up to a computer, that's really your only cue that everything was successful. And the fact that the robot will start driving and avoiding obstacles. Some motor functions. A lot of these motor functions, they might be slightly adapted, but a lot of the starting ones anyway are just pulled directly from the SparkFun Inventor's kit code for Circuit 5C. So in which case, I have a function called stop all the motors, where I just write all of the inputs 1 and 2 for both motors low, and that stops the motors from going. I've also done the analog writes to the PWM pins and wrote them 0, indicating 0 speed. This is kind of redundant, not necessary, because when your direction pins are both set to low, it doesn't matter what your speed is, the motor won't move. So this is kind of redundant, but still good to be explicit and just keep the code consistent, because you'll see in the other code I am always writing to the speed. So I do see why they did that. I've commented out all the serial communication stuff simply for the fact that I'm not going to be using it. So if you want to drive the motors forward, the logic is that you set the input 1 pins for both your motors, so the left and right motors. You set the input 1 pins high and the input 2 pins low, and that drives motors forward. When the input 1 is high and input 2 is low, that drives the motor forward. And then you just call the analog write on the PWM pins with the speed that got passed in. And you'll drive the motors at that speed. To drive the motors backwards, you do the opposite. So you write the analog input 1, not analog, channel A input 1 pin low for both motors, and the input 2 pin as high. So when input 1 is low and input 2 is high, that's driving the motor in reverse. And then again, just drive at the speed. To turn right, again, you take in a parameter of type in for the speed, and you drive one of the motors, I guess the left motor, motor A is the left motor here, you're going to drive it backwards by having the input 1 low and input 2 high. Driving it backwards. As I'm reading this, I think I changed the code. So the code I know works, but I think I forgot to change the comment or something, because motor A would not be the left motor. So don't focus so much on the comments here, and just focus on my words for a second. If you need to turn right, so if I need to turn right, whatever way you're turning, you always want that wheel to go backwards, and you in reverse, and you want the other wheel, i.e. in this case the left wheel, to go forward. So this is saying that this is the left motor, but this is fact must be the right motor, because this one is going backwards, because again, remember, when input 1 is low and input 2 is high on a motor, that's driving in reverse. But if I'm turning right, the wheel that I want driving in reverse is the right wheel, because I want that spinning backwards in order to give me a tight turning radius. So this must be the right wheel. And this wheel is driving in the forward direction because it's got input 1 is high and input 2 is low. So that is going forward. So that shouldn't be the right motor. That should be the left motor. So again, if I'm turning right, I want the right wheel going in reverse, and I want the left wheel going forward. And then just set the speed. So I'm assuming the comments are off here for the turn left as well. So yeah, for turn left, I have my left motor going forward, indicated by the high input 1 and the low input 2. But again, if I'm turning left, I want the right motor going forward, and I want the left motor going in reverse, i.e. with input 1 low and input 2 thing. So these are just mixed up. Motor A is the right motor and motor B is the left motor, I guess. But again, don't focus on the comments, just focus on whatever way you want to turn, you need that wheel to go backwards and the other one to go forward in order to get you a really nice turning radius, a tight turn. I apologize for the confusion there with the comments. This is these are functions now I've created called increase speed, where I basically say if the current speed plus the speed increment, which is a constant I have representing, I believe, 25, if the current speed plus the speed increment is less than the max speed, which is 255, then I'm going to increment the current speed by speed increment. Else, meaning if it's not less than max speed and I've either reached max speed or I'm past it, I'm just going to set the current speed to max speed, because again, I need to cap the speed at whatever the max speed is. So that's just increasing my speed, and then I call the set motor speed function passing in current speed. So I'm just going to set my current speed function. Now this function doesn't really do much. I'm going to just go look at it right now. Yeah, the set motor speed function just has one line of code. It takes in a parameter type speed and it assigns that parameter to motor speed. So you could argue that this function is not really necessary. A little helper function. I think I was originally doing some print screens and different stuff, so I did create this. But there's an argument to be said that, you know, it's good coding. It's nice to still have a function there to be explicit what's happening. Oh, I'm setting the motor speed to current speed. But this would be probably just as explanatory. So, you know, each their own. But that's what I'm doing. I'm setting the motor speed to the current speed, and then I'm going to output that via the serial monitor. I'm doing the same thing for decrease speed. Works on a similar logic. As long as I'm above min speed, which is 0, I'm going to decrement the speed. If I reach 0 or below, I'm just setting the current speed to min speed, and then I set the motor speed to that speed and output to the console. Set motor speed is just doing this one line of code. It's really just a helper utility function, probably not overly necessary. Test drive. This function is basically just doing a function test. I included this once just to verify the motor and everything was working. I can press a button on the remote control and it runs through a couple things: driving forward, stopping, driving backward, turning right, turning left, stopping the motors for a certain amount of time. It's really just doing a function test to let me know everything's working. You can pause the video and look at that in greater detail if you want. I do make calls to a lot of my functions within this test drive function. So again, you can see how modular my code is. It's a fairly big function, this test drive. It's doing a lot of different things, but really the code could be a lot worse. It could be a lot longer, but instead I'm making so many calls to other functions within this test drive function. So I'm calling the drive motors forward function. I'm calling stop motors function. I'm calling drive motors backward function, increase speed function, decrease speed function, turn left, turn right. So a lot of other functions are called in here. That's why I love modular coding. So what is that turn right and turn left? Well, we'll see shortly. First, we have a function called right motor. It takes in a parameter of type int, representing the motor speed. If the motor speed is positive, hey, I want to drive forward. So my input 1 should be high, and my input 2 should be low. That drives me forward. If my motor speed is less than 0, meaning it's a negative number, well, I want to drive backwards. And that's indicated by having your input 1 low and your input 2 high. Else, well, if it's not positive, it's not negative, that means it's 0. If it's 0, both inputs are 0 and I won't move. So again, in that case, you don't even need to write the PWM, but no matter what, I'm doing my directional control here, and then I'm doing my speed control by calling an analog write, passing in PWM and the absolute value of motor speed. So motor speed, when you're sending in a signal to a PWM pin on the Arduino, analog write only accepts values between 0 and 255, all non-negative values. So if my speed happened to be negative when I came in here because I was driving backwards, well, I can't throw in a negative value in my analog write. So I just need to call the absolute function and make it an on-sign number, so it's not a negative value. Left motor works the exact same, it just works for motor B. So again, if I have a positive value, I'm going to drive forward on motor B. Negative value, I'm going to drive backwards. Else I'm going to stop, and I'm going to write my speed here. So again, directional control are the digital write functions, and the analog write function to a PWM pin is doing my speed control. Now moving on to driving mode functions. So these functions are the bread and butter of controlling what mode I'm in when I'm running the function. Correction, the program. So the mode that the program starts in is the autonomous mode, and that is taken care of by, well, as we can see, autonomous obstacle avoidance logic using non-blocking code is what the run autonomous mode does. So right away we set the current mode to autonomous, again using that enum type that I've created. So this is like 0 under the hood, so I'm setting the current mode to 0, but using this enum constant. And then this is all logic to help me track the state I'm in, like the state of the robot, what state it is in. So again, tracks the time of the last action, tracks the current state of the robot, tracks whether the robot is reversing or turning, and that's all this function is doing. It's allowing for efficiency and allowing me to not repeat code unnecessarily. You might notice that they all have this static keyword in the front. That just basically means that the value of these variables will persist throughout the calls to run autonomous mode. Meaning every time I come into the function, it doesn't restart as a new value. It persists throughout the code. I've talked about static functions in more detail in other videos, so if you have questions, feel free to post them. I'll be happy to answer. But that's essentially what it's doing. The static... actually, you know what? I'll just quickly jump out here and show you some of my code choices. So the significance of static local variables, so this is in my code design choices section, is that static local variables retain their values between function calls, differentiating them from regular local variables, if I didn't have that static keyword, which are then reinitialized every time a function is executed. So basically, my last action time would be reset to 0 every time I entered that function. By qualifying it with the keyword static, the variables retain their values between these calls. So this means that last action time is initialized once, and its value persists across all calls to the function. So the reason I'm using it is for state tracking. The static variables allow a function to maintain its own internal state, which is essential for the tasks that need context between calls, e.g. timing and state machines. More on that online. And it's just really for efficiency. So I'll get back to my code here. So that's what I'm doing. And when I say it's keeping track of its own internal state, well, what does that mean? Well, let's keep going in the code here. I'm grabbing the current time using the millis function and setting the current time. Again, I've talked about time functionality a lot in the past, especially with regard to debouncing. And then I'm calling the measure distance function, which uses the ultrasonic distance sensor, and I'm getting the distance. So that's what I'm doing right away. I'm getting the current time and I'm getting the distance. And now here's what is happening. I'm going to be in state 0 when I first come into this function. So I'm going to check for an obstacle and decide action. So I'm driving around in autonomous mode, and if the current state equals 0, which it will be at the start, then I'm going to come in here. And if the distance So I'm going to be in state 0 when I first start the program. If the distance is less than the obstacle threshold, so the distance I measured to some object, if that's less than the obstacle threshold, which I believe I had set 25 centimeters, then that means an obstacle is detected and I need to start reversing. So I'm going to call the drive motor's backward function, passing in my motor speed. And I'm going to set my static Boolean flag up here to true. Is reversing true? Yeah, I'm reversing now. I'm driving backwards. Am I turning? No, just reversing. And then I'm going to set my last action time, again, one of my variables up here, to the current time. And now I'm changing the current state. So again, one of my variables, current state, which tracks the current state of the robot, I'm changing it to 1. So I started in state 0 when I was just driving around. Right? Now, there's an obstacle in front of me. I start driving backwards. I'm changing my state to 1. Because now I'm in the reversing state. I'm in a different state than I was before. Before I was just driving around. As soon as I'm detecting an obstacle, I'm in a whole different state. I'm in state 1. Now, if I had never detected the obstacle, if distance less than obstacle threshold, if this wasn't true, meaning there's no obstacle in front of me, or at least not close, then I would have no obstacle and I just keep moving forward, drive forward. So I only change the state once I detect an obstacle and I start driving backwards, where I set is reversing true, is turning is false, and I make my state 1. Now what happens? Well, that means now that my state's 1, when I keep going in the code and I come down to this if statement, if current state equals 1, and is reversing, which we know it'll be true because we just set it true if we had an obstacle, if that's true, then I come in here. However, I only execute this code after a certain amount of time. If the current time minus the last action time is greater than 500 milliseconds. And what's the whole point of this? Well, this means that when I first detect an obstacle, I would have came in here, I'm going to set reversing true, and I'm going to set my state to 1. So right away, this is going to be true, and I'm going to be in here. But I don't want to stop. I need to reverse for a certain amount of time. I need to reverse for, well, in this case, 500 milliseconds, half a second. So I don't want to do anything else until that time has passed. So even though this will be true right away, I'm not going to enter this if statement, this nested if statement, until I've been reversing for 500 milliseconds, half a second. Once that's true, I'm going to stop reversing and start turning. So I'm going to call the turn right function. Is reversing is now false. Is turning is now true. So I set that Boolean flag to true. Again, I set the current time to last action time again, because again, I'm going to need a delay. And then I set the current state to 2, because now my state is that I'm turning. So the robot is keeping track of its internal state, which is a very important thing to do. So now state 2, turning for a specific time. If the current state equals 2, which it will be, after 500 milliseconds going backwards, and is turning is true, which it will be after I've reversed for 500 seconds, then I'm going to stop turning and go back forward again. Now I think I've avoided the obstacle. I'm just going to go back to driving forward and set is turning to false. So now both is turning is false and is reversing is false, and I'm going to be back in state 0. So that way if I come back into the code, I start it all over again. So that's why these functions are static, so that as I'm running through and keep going in and out of autonomous this function, I don't just constantly start back at 0 every time. I appreciate this video is getting pretty long, so I'll try to speed it up. I'm trying to go thorough, but I'm just, again, if you've watched my previous videos, you've heard me advocate for myself against being a YouTube content creator. I'm not really good at this, but I'm trying my best, so if you have any questions or comments, feel free to post those. In the run IR remote mode, it really does the same thing that we were doing in the loop function from the start. We're simply going if there's anything, if we've just received a signal via the IR remote, then we're going to process the IR command by passing in that command, which this will give me the hexadecimal version of that command, and then always resume. This just basically tells the code to say, hey, prepare to receive another IR signal in the future. You always have to tell it to resume. So that code's fairly simple if you've followed my previous videos on IR control, or just look up the documentation. And then this function, run RF transceiver mode, what this does is this basically prompts the user to enter a distance, although we won't see that because we won't be plugged in, but it tells the user to enter a distance, a direction followed by a distance. So the direction would be forward, backward, right, left, and again, you just have to put the first character in. And then, and toggle as well is one of my options, to toggle an LED. After you do that, it's going to be followed by a distance. So for example, F, in this case space 50, but I actually am using a comma as a delimiter. So I'd have like F comma 50. And that would say, hey, I want to go forward 50 units, which should translate to 50 inches. And so that's all the prompting I'm doing for the user. That has nothing to do with the radio so far. That's just serial communication. But what's the radio? Well, if radio.available, just like if serial.available, same thing. If radio.available, hey, is there anything for me to receive? Am I receiving anything wirelessly on the radio? If I am, I'm going to go radio.read. I'm going to call the read function. And whatever I read, I'm going to store it in this char one-dimensional array, i.e. this C-style string. And why am I making this char one-dimensional array size 32? Because the write function, this is the read function, but the write function associated with the transceiver, or correction, the transmitter, can only write 32 bytes at a time. So you can only write 32 bytes at a time. So because of that, I am only able to read 32 bytes at a time. So that's why I've made this char one-dimensional array a size 32. This C-style string, or char one-dimensional array, however you want to think of it, this is the largest it needs to be because it can't receive anything more than this anyway. I'm only going to be able to have the write. Anything that's being written to me is going to be no bigger than this. So again, I'm using the radio.read function. Whatever I read, I'm going to assign it by reference. I'm going to assign it to this variable that I've created right here. And you always have to include the size. Again, if any of this is unfamiliar, feel free to post something in the course form. But really, I've went over the RF transceiver modules in great detail in previous videos, so I just don't want to harp too much because this video is already well over an hour. So once I do receive the command, I read it in, I sign it, I store it in receive data, this C-style string, and then I'm going to call the parse command function. And you'll notice I didn't just pass in receive data, I'm actually wrapping it in this string function. So I'm taking the C-style string and converting it to a C++ style string. And the reason I'm doing that is simply because the parse command function that I've created takes in a C++ style string. So I could rearrange either the function to accept a C style string, i.e. char one-dimensional array, or I could just wrap the C style string in the string variable. And that's what I've chosen to do. Lots of different ways to accomplish the same thing. So after I parse the command, ultimately what that's going to do is that's going to assign a value to my bot direction, the direction I want to go in, and the distance. So these are two global variables I have up. I've shown you earlier. Might as well just go back really quick just so you can see them. Right here. So very early on in the code, the bot direction and distance are, again, just track the direction that the robot's going to drive in and the distance to travel. So that's I think I skipped my spot. There you go. So that's what's happening there. I'm passing in that direction that I got into this function execute radio command that we've created. And then control LED mode. This is just setting up, lighting up the applicable LED for the mode that I'm in. So I take in a mode object, remember, which is that enum class I created. This is a non-value returning function, and I simply check what mode I'm in. If the mode equals autonomous, and the last LED state is not equal to green LED, this part of the code is just for efficiency purposes. Really, I just need to know what mode I'm in. If I'm in autonomous mode, I'm going to turn the green LED on high, and the red and the blue LEDs both on low. But the green LED is going to be high in autonomous mode. And then the other stuff is for efficiency. I'm assigning the green LED to the last LED state, and then printing out what mode I'm in. If I was hooked up to a computer, I'd be able to see this on the serial monitor. But I'm assigning the green LED to last LED state. The reason for this is that way I only want to execute this code if I have a change in mode. If I'm stuck in autonomous mode for a while, I don't want to keep coming in this code every time and doing these 3 digital writes. You know, I don't want to write the red LED low and the blue LED low and the green LED high every time I run this loop, which will be a lot because I mean the microcontrollers are quick. I don't want to run these executions of code every time if I'm just staying in autonomous mode. I only want to run them if there's been a state change. So again, if the mode is autonomous and the last LED state is not equal to green, meaning there's been a change of state, then I'll turn the green. But I won't do it if I've already been, because like when I come into this code the first time, as you can see, I set the last LED state to green. So the next time I come in this code, I'm like, and I'm still in the autonomous mode, oh, I'm going to go if mode equals autonomous, great, halfway to true. But remember, for a Boolean, when you have a Boolean and statement, both sides of the ampersands of the operator, the AND operator, need to be true for you to execute the code. So I'm still in autonomous mode, but is my last LED state not equal to green LED? No, because my last LED state I set to green LED this time. So I'm going to go last LED state not equal to green LED. Well, this is false. It is equal to green LED. So I'm not going to come in here and re-execute the code. So it means I only execute the code when I'm in autonomous mode and my last state was something besides green. And it will be when I've switched modes and I've come into autonomous mode from another mode. But if I've already been in autonomous mode, last LED state is green and I won't come in here. So it's adding a little bit of confusion, this extra little bit. I could have just gone if mode equals autonomous. That would have been fine. And I just would have executed these 3 lines of code, these 3 digital writes every time. I added this extra little bit, this state tracking, to track what state I am, just so I only ran it once when I change modes. And the similar code is happening for the other states. Else if mode equals IR remote and last LED state is not equal to red, then I'll come in and do these digital writes. So again, if I'm in IR mode, I want to digitally write the red LED high. So I want to turn on the red LED on and turn off the green and blue. And I'm assigning red LED to last LED state. Again, why? So that I don't execute this code again while I'm staying in IR remote mode. The RF transceiver mode is a little different. So I'm going elif mode equals RF transceiver. You notice I don't do that state thing because I've got a little different things going on here. I want to turn the blue LED on high. That indicates that I'm in RF mode. I want the green LED low. Blue LED high, green LED low. The red LED is a little different. Normally I just want it low because I want the blue LED on, indicating I'm in RF transceiver mode. However, one of the commands I do when I'm in RF transceiver mode is toggle a red LED by sending the letter T. So because of that, sometimes I want the red LED on. So I simply have this little if-else statement. If the red LED toggle, if this Boolean variable is true, oh, turn on the red LED. If it's false, turn it low. And again, I did do this blue LED equals last LED state. Not really necessary in this case because, and I could comment this out, but this is a PDF, so I can't. But I obviously had this as a remnant from when I was not doing this toggle thing, but then I added this toggle code, so this code no longer is necessary. I apologize for that. So moving on. The ultrasonic functions for the HC SR04. This measure distance function, this is straight from the code from, I think, SparkFun. I have other code where I don't use the pulse in function. I use timing functionality, non-blocking code. I think that's better, but this is the one that comes with the library, and this is kind of the standard one to use. So how does this work? Well, I do a digital write of the trigger pin low for 2 microseconds. That's not overly necessary. It's just more or less making sure that ultimately what I need to do is send a high pulse for 10 microseconds on the trigger pin. So digital write trigger pin high for 10 microseconds and then low. This is really the code I need. But the only reason I put it low first for 2 microseconds, or that I think SparkFun did this, I think this is their code. The only reason that's done is to ensure that you have a low signal before the high signal, so that you know the state of the signal before you do what your actual work is. So this is just to put things in a known state, i.e. low, and then actually do your digital write on the trigger pin high for 10 microseconds. And then, so the trigger pin is an output pin, writing that 10 microsecond pulse, and then the echo pin, you're calling the pulse in function on echo pin, passing it high as your second argument, and that's just based on the HC SR04 ultrasonic sensor. It expects a high pulse. And then this is going to return a duration, which we're using along as our data type. This returns a duration which is proportional to the distance an object is in front of the ultrasonic sensor. And how do we calculate that distance? Well, we take that duration and we times it by 0.034 divided by 2. If you look at the data sheet for the ultrasonic sensor, or if you watch my previous videos, I kind of explain in detail how this is actually calculated, in a lot of detail actually, but I'm not going to go over that here. Suffice to say, we take the duration, times it by this value, and it gives us a distance in centimeters. If we wanted it in inches, it'd be a different value that we'd be multiplying by. But this gives us our distance, and ultimately, that's what we want to return. So this whole function, measure distance, is so that we can return the distance. The RF transceiver functions, is basically, I've explained this in greater detail in other videos, so I'll just try to be quick. This initialize function takes in two arguments. It takes in the mode that you want to be in, whether that's receive or transmit mode, and the address. I'm using default arguments for both, so you can call this function and not pass any arguments if you want, and it'll automatically be set up to receive mode and to the address that we've already created above, up in our variables. And that would work for me because I do want this in receive mode. I did actually call it, I believe, with I called it with receive, but I didn't have to. So, and I'm not sure if I actually did, so I might have just left it blank. So again, I could have called this init radio function up in setup and not passed anything in, and the default arguments would initialize it as a receiver with the default address, just like I want. The function returns a Boolean, and the reason for that is it returns true if there was successful initialization, false otherwise. So if radio.begin, if that returns false, meaning it doesn't initialize, well, the Boolean not operator, not false, is true. So if the radio doesn't initialize, I'm going to print that out to the serial monitor, and then I'm going to return false, because again, this is a Boolean return value. Otherwise, assuming I did get set up properly, I'm going to move on. I'm going to set the power amplification level to max. I don't need it max. I'm in my living room. Min would have been fine here. Min, low, either of those constant variables would be fine. But I did it max. If you're outside and you really were at the limits, the upper limits of your 1,000 meters or 100 meters if you're using the internal antennas, you want to put more power towards it. However, this comes at the detriment of the higher the power amplification, the more power your modules are using. So, you got to factor that in. However, the claim to fame for these NRF24L01 modules are that they take an extremely low amount of current. They're really good, especially compared to like Wi-Fi modules. They're really good. The set retries function simply the first argument can be from 0 to 15, and it represents multiples of 250 microseconds. So 3 times 250 microseconds is 750 microseconds. It represents the time you want to take the delay between retries. And this second argument can be between 0 and 15, and it's the number of retries. So in this case, I'm saying I want to retry to initialize, the radio. I want to retry 15 times, and I want to wait 750 microseconds between retries. Obviously, the more retries you have, or the more time you wait, the higher this first argument number is, from 0 to 15, the more stable your radio connection might be. And then I just do a couple if-else ladders. So if string compare, this is using C-style strings, if the string compare of mode, the thing that got passed in right here, if that and tx equals 0, meaning if your mode you put in was transmit, well then you're going to set this up as a transmitter. You're going to radio.open writing pipe, and you're going to write to this address. And radio.stop listening, because you're not listening, you want to stop listening because you're transmitting. That's if you're in transmit mode. We're going to be entering receive mode in this case, so I'm going to open the reading pipe, and it takes in two arguments. The first one is from 0 to 5. It represents the pipe that you're listening on. And the second one is the address, the same as transmit. And again, I'm just typecasting it to UNT 810. This is just for efficiency purposes, as I mentioned above. But if I'm in receive mode, I'm opening reading pipe, not writing pipe, and I'm start listening. I'm calling the start listening function, not stop. So transmit, you're writing and you're stop listening. Receive, you're reading and you start listening. Else, someone entered an invalid command, and I just let them know, and I returned false, indicating, I wasn't able to initialize the radio. Someone typed in, cheese. So there you go. I flashed the blue LED 3 times, just indicating successful initialization of the radio, and I output that to the serial monitor if I happen to be hooked up, and I return true. The execute radio command function, again, as we've seen earlier, it takes in a string, a C++ style string. So string is a type associated with the Arduino programming language. So we take in a string for bot direction, and this code is a little bit confusing. I rearranged this code quite a bit, more or less just for experience, so something to do, and try to get a little efficiency to it, simply for the fact, I'll show you the original code. So the original code that comes with the SparkFun Inventor's Kit Guide for Circuit 5C has this bit of code here. Let's take a second for that to catch up with us. So, where is it? Oh, correction, this is not the correct code. I'm thinking of the code for 5B. So this is the SparkFun Inventor's kit code for circuit 5B. And just bear with me. So this code here, we have if the bot direction equals F for forward, we do some stuff. If it's B for back, we do some other stuff, right and left. You'll notice that the last 3 lines of code in all cases are the exact same. So right there, when you're repeating code over and over and over, that's typically not good programming style. Not only is that the same, but the other 2 functions at the start are always calling the right motor function and the left motor function. The parameter arguments being passed in are just different. So I'm passing in 200 here, so positive speed because I want to go forward. Negative speed values here, just the same magnitude of speed, just the negative versions because I want to go backwards. And similarly here, we're just switching the numbers out, sort of thing. So a lot of this code is repeated. This is very easy to understand reading it, but it's long, in my opinion. And again, it's just a lot of repeating code. So I decided to see if I could change that up by not repeating so much code, but it does come at the detriment of, maybe not being as reader friendly, so to speak. So this is, I'll just shrink it here, this is the code there. But it is, maybe not as readable. You might have to parse it a little more to understand what's happening, but it's more efficient in my opinion. But I mean, I might be biased because I made up the code. But let's just take a look at what's happening. So right away when you come in the function, I'm creating a couple local variables for speed and left motor speed and right motor speed. I assign 200 to speed, and then I assign that same value to left motor speed and right motor speed. And again, this could even be done more efficiently now that I'm looking at it, but I think I did these on separate lines so that I didn't make this more confusing than it already was. And then I'm going to go if bot direction equals F, then I'm going to assign speed, which is 200, to right motor and left motor. So now the speed when the direction is forward is 200, which, if you recall, is the same it is here when the direction was forward. And then else if, so again using else if, because again this way only one of the functions will execute, if, else if, we only want one function to execute in these cases. Else if the bot direction equals B for backwards, I'm going to assign negative speed. So I'm going to just negate the speed by putting a negative sign in front of it. I'm going to assign that to right motor and left motor, which again is the same as the code here. It had the same magnitude of speed, just the negative versions. And then for right, else if the bot direction is left, right motor is 255 and left motor is negative speed. So again, because if you're turning left, you want the left motor, whatever side you're turning to, you want that wheel going backwards. And you want the other one going forward at full speed. That gives you a really nice tight turning radius. The opposite is true for when the bot direction is in going right for R. We want the right motor to be the reverse speed and the left motor to be going full out so that we have a nice tight turning radius. Otherwise stop, and if the bot direction equals T, I'm going to toggle a red LED. So, but these are extra code I added. But this code here is trying to simplify the other code. Well, not simplify in the way it's read, but just make less lines of code more efficient. And then no matter what happens, when I come down here, I call the same 5 lines of code. I write the motor speed, I make the right motor written at motor speed, whatever the right motor speed is, which got assigned up here in these if-else statements. The left motor gets assigned left motor speed, and then delay is the drive time times the distance to drive, the distance that got passed in. I convert that to an int and times it by drive time, that's the delay. And the right motor and left motor get written to 0, no matter what. So this code is, longer, but it's arguably a lot easier to read and understand. I agree with that 100%. I just wanted kind of an exercise in modifying code and making it a little more efficient so I wasn't repeating code. There's no code repeated here. I'm just kind of, doing some logic to figure out what I need to set things to, and then calling this code, this function, once. It just has different values. So hopefully you could see that. I got these if-else statements basically deciding what bot direction I'm going, if I'm going forward, back, left, or right, and I assign values to the left and right motor speeds accordingly based on that, and then I only have to call the function, these 5 lines of code, once. They just will have different values. And just to go over this line, what's happening, we're calling delay of drive time times distance dot to in. Remember, distance is one of our variables. Bot direction is one of the values we got when we read in from the RF transceiver, and we also got the distance. And both of them were passed in as strings. This we're using as a string, so there's no issue. This we need to convert it to an int. So we're going to go distance, which is a string, and we're going to call the toInt function on turning into an actual integer representation of whatever the string was. And then I'm timesing it by drive time, so I can delay my time for a certain amount. Now what is drive time? I'm just going to jump right back to the start. Drive time was this variable here, if you recall. It's the number of milliseconds that it takes to drive 1 inch. So if you tell the robot to drive 25 units, it should drive about 25 inches. Again, as this comment states, you might have to change these numbers based on your motor tolerances, your floor that you're driving on, the friction, but that's where the drive time comes in from. So that's what's happening here. I'm delaying for the drive time times the distance you passed in, so hopefully I drive the distance that you're expecting. The last command associated with the RF transceiver module is the parse command function. And we might as well just read my Doxygen comment that I created here. Again, Doxygen comment has these little at things, so at brief. Well, what's the function do? Well, it parses and processes incoming commands. Okay, a little more detail, please. Well, it parses and processes incoming commands sent wirelessly via second UIC and fitted with a second NRF24L01 module. So again, you're parsing and processing incoming commands sent wirelessly via a second microcontroller that is fitted with another RF transceiver module. And this microcontroller module are connected to your laptop, separate than the microcontroller and NRF24L01 module that are on your remote control car. The command will be in the form of a single character representing a direction, like forward, left, that sort of thing, and then optionally followed by a comma and an integer representing the distance to travel. So for example, we could have F, 50, L, 100. So the first character is indicating the direction, forward, left, right, back. And then optionally, we might have a comma followed by a number representing the distance. I say optionally because you could just have T for toggle LED, and you don't have a comma and a number afterwards. But that's what this command does. So it takes in a string command, and again, we've seen that up here. I'll just show you again where this is being called. Parse command right here. So when I read in a command wirelessly that I received via my RF transceivers, I read that in, stored it in received data, which is this C-style string, and then I call the parse command function, passing in received data, that C-style string. I just wrap it with this function string, which converts this C-style string right here into a C++ style string, which is what my parse command function expects. This parse command function will ultimately set the bot direction to whatever it is that I can then call in my execute command function. So back to the parse command function. So I'm taking that string in that I would have received wirelessly, and then I'm going to grab the first character from that string. So command.char at 0, give me, because a string is really just, again, a one-dimensional array of characters. So I'm just going char at index 0. I'm grabbing the character, the letter, at the first index of a string. So if this is a string, this is really a character array with the elements f, comma, 5, 0. And index 0 is f. So I'm going to grab that and assign that to the bot direction. So my direction is f, or it could have been L, or it could have been T. And then distance is I go command.substring index2 dot toInt. So I'm calling a substring function, passing in a single parameter. When you pass in a single parameter, it goes to that index and then reads and gives you a substring from that index all the way to the end. If you pass in 2 parameters, you do a subset, but that's not what we're doing here. So substring at index 2, well, I'm going to go to index 2. So the index 0, the comma is index 1, index 2 is the 5 here. I'm going to get a substring from 5 to the end of the string, which is there. And I'm going to take that string, 50, I'm going to call the toInt function on the string, turning it into an actual integer value, and I'm assigning that to distance. And there you go. So now bot direction and distance are both global variables. Now they're both set to whatever they need to be. That way I have access to them. For example, I have access to bot direction in my execute radio command function. And then toggle red LED. This is another function associated with the radio transceiver module. And this is just a function I created that allows me to toggle the state of the red LED. So again, red LED toggle is just a Boolean flag. And I just, every time I access this function, I'm just toggling the state, on, off, on, off. RF transceiver functions, or correction, IR receiver functions are as follows. I handle IR commands. Basically, I take the command in and I just verify what the command is. If the command equals command autonomous, which again, these are just constants I created representing different commands, I believe. Well, let's just go look quickly, just so you guys are tracking where these came from. So at the very start of the code, under the IR receiver code, I've created some constants, some UN16T constants. Again, this is just for efficiency. You can think of these as ints, really. I've created constants. Command autonomous is associated with the hex value B0. IR is associated with the hex value 44, and the command RF transceiver is associated with the hex value 72. This corresponds to my play button. This corresponds to the select or OK button on my remote control, and this corresponds to just some red button with a dot on it on my remote control. So, the handle IR command function, it takes the command in, and if the command equals command autonomous, then I'm assigning autonomous to the current mode. I'm just setting my current mode to whatever the command is. So if the command equals command autonomous, meaning if the command is the hex value 0x B0, meaning I press the play button, well, then I want the current mode to be the autonomous mode. And I'm just going to print that to the console if I happen to be attached, which I'm not going to be. But else if command equals IR remote, again set the current mode to IR remote, output it to the console. If the command equals command RF transceiver, update the current mode accordingly. Else just print out the command. I don't know what the command is, but I'm going to let you see it. Process IR command. This processes IR's commands when access is granted. So if access is granted, meaning if I'm in IR remote mode, I'm going to take in the command, I'm going to print out the command in hex so you can see what it is, and then I'm just going to use a switch statement to decide what to do. So it's a fairly long switch statement. I'll just zoom out a little bit. Those are all the commands. So if I press the play button on the remote control, it sets the robot car into autonomous driving mode. So again, if the command is the hex value 0xb0, which is just the value associated with my play button, then the current mode is going to be autonomous. If you typed in the command 0x44, meaning you pressed the, this comment is wrong, I believe 44 is actually associated with the middle select button. If you've pressed the middle select button, not this red button, then it sets the car to the IR remote control mode, and I set the current mode to IR remote control. If you press the 0, if the hex value is 0x72, meaning you've pressed a blue button with 4 dots on it, I'm going to toggle the blue LED on and off. That's just for fun. and I'm going to set the current mode to RF transceiver. And again, all these, I'll let you pause and read this in detail on your own time. This video is incredibly long. But basically, the volume up button will cause the speed to increase. The volume down button will cause the speed to decrease. The up arrow will drive me forward. The down arrow will drive me backwards. The left arrow will turn me left. The right arrow turns me right. If I press either the stop or pause buttons, you notice I don't have a break between these. So either the stop or the pause button will cause the motors to stop. If I press the blue button with the 4 dots, I'm going to toggle the blue LED on and off. Again, I think I made a mistake up here in my comments, so don't worry about that. If I press the green button with 2 dots, I'm going to enter the test drive mode. And again, normally I would be going back and forth showing you the circuit, or my remote control, so you could see the buttons and stuff that I'm talking about. But again, I'm having technical difficulties with my wireless webcam, so I'll have to show you guys that after. But trust me, these buttons exist on the remote control. So basically, all this switch statement is doing is seeing what command you typed in, i.e. what button you pressed on the remote control, and then doing something applicable, like calling an applicable function to do that action. So that's an IR remote control mode. And then finally, I just have a toggle blue LED function. This works identical to another one of my functions, I believe, toggle red LED. I could have made one function a pass-in parameter. I just named 2 separate functions. All I do is I toggle the state of blue LED, and then I do a digital write to the blue LED pin of, and I'm using a ternary operator here, or conditional operator, where blue LED state, as we know, is a Boolean variable. And so if this is true, I'm going to do what comes after the question mark. I'm going to output high to my digital write, so I'm going to turn the blue LED on. If blue LED state is false, if it evaluates to false, well, I'm going to do what follows the colon, and I'm going to digital write low. So again, if blue LED state is true, turn on the blue LED, otherwise turn it off. And that is all the code for the receiver, and that's the bulk of the code that we're going to go over today. The transmitter, really simple. I've went over the RF transceiver modules in detail in other videos, so I'm going to try to be really quick. I know I say that a lot, and we're already coming up in 2 hours, but this is the transmitter code. It just deals a lot of stuff with the same stuff for the RF transceiver. I need to include the library, create some constants for my CE and CSN pin, call the constructor for the radio, passing in the CE pin and CSN pin. Same address, which is just a char one-dimensional array, a C-style string. Same address as the receiver. The init function is almost identical. There is a slight difference here. The other init function I created, I returned a Boolean. This one, I have it as void. Sometimes when I'm writing functions, I don't always copy my code. I just kind of rewrite them for practice. I obviously decided to make this void, but they're essentially accomplishing the same thing. Maybe I will pull up that code, just so you can see the difference. I'll just pull up the actual code here. So this is the init function in the transmitter code, and this is the init function. Let me just pull up the init function here. So under motor functions, I could go Control F, but instead I'm just going to scroll under driving mode functions, under ultrasonic functions, and our transceiver functions. So here's our init code. So I'll pull it past the comments so we can compare. So you can see in the transmitter function, it's a void return. It's Boolean return here. But they're both taking in kind of the same things. This is taking in a string passed in by constant reference for mode, and this is, I'm taking in a pointer to a char, so a C-style by constant still. So this one I'm taking a C-style string, a pointer to a char, which is a C-style string. This one I'm taking an actual string, because string is a type in Arduino. But either way, I'm passing in the string by constant reference, and its parameter name is mode. Here I'm passing in the C-style string, the pointer to a char, by constant, and it's still called mode. This one I don't have any default argument for mode, so I actually have to explicitly say transmit or receive when I call this function. Here I have a default function set up, so if I don't enter anything, it'll be set up in receive mode. The next part is the same. I'm passing in a pointer to a char, a constant char pointer address, and it has a default function. Same thing here. In here, I'm checking to see if radio.began was successful. If it wasn't, I'm going to enter a forever loop, while 1, and just halt the program. Here, if it's not successful, I return false. I don't enter a forever loop. Here, I'm halting the program, and I'm just stopping. Here, I'm returning a value, false. That's why the return type here is false. Here, I'm not returning anything. I'm just halting the program. Ultimately, in either case, if I move on, here, I'm setting the PA level to max, the power amplification level, and I'm setting the retries. Here, I'm setting the PA level, and I'm not calling setting retries. Again, you don't have to do that. If your radio doesn't set up the first time, it might not set up the other times anyway. So this is kind of, a nicety, not really required. And then in both cases, I'm doing the same thing. Here, because I passed in a C-style string, I need to compare the C-style string using C-style string commands. So if str compare, the compare function that takes in mode, and the string literal tx, I'm comparing these. If they're the same, it equals 0. That's how the C-style string command, string compare works. So this is associated with C-style strings. Because in this case, I'm actually using an Arduino string type, I'm just simply, the equality operator works with string type, so I can simply go if mode equals transmit. So these difference in codes are literally doing the same thing. I just wrote them differently, because I wrote them at different times, to be honest. So if mode equals transmit, again, I'm opening the writing pipe, passing in the address, typecasting it here for efficiency. I'm stop listening, I'm calling the stop listen function, and then I'm just outputting, hey, radio set to transmit mode to the console. Else if mode equals Rx, and again, I can use the equality operator because these are both strings of string type. Then I'm going to go radio.open reading pipe, passing in my 2 arguments, 0, which is a special pipe, I've talked about that before, and the address, which should be the same address as the writing pipe. And I go radio.start listening and output that to the console. Otherwise, it's invalid. If you've entered an invalid thing, I'm going to go while 1. I'm going to halt the program. So I halt the program if the radio didn't initialize, or if you wrote something invalid. That's why my return type is void. I'm not returning anything. Here, if you wrote something invalid, I return false. So obviously my logic in the program here is a little different, and I ultimately halt the program if this returns false, I think. So it's just a difference here. I'm returning a value, and then externally from this program, I'm halting the program. Here, I'm just doing it within the init function. So that's how that works. But again, the differences are very minute. But I do like doing things differently for educational purposes to show, again, there's more than one way to do something. Here, I'm passing in an actual string. Here, I'm passing in a pointer to a char, so a C-style string. This is more of a C++ style string. Here, I'm returning void. I'm not returning anything. Here, I'm returning a Boolean variable. So here, if the radio didn't initialize or someone entered something invalid, I return false, and I let the calling program, the calling function, take care of doing whatever it's going to do, which is ultimately probably going to halt the program. Here, I'm not making the calling function do that. I'm just halting the program. So those are some minor differences. I figured they just merited a mention. So I just went over all this. Handle serial input function. This does what it sounds like. It handles the serial input, because this is on the transmitter side, remember. So if serial.available is greater than 0, meaning verify that I've typed something into the keyboard, if that's true, then I'm going to do serial.read until next line. I'm going to read the entire line and assign it to the string variable command. I'm going to trim any white space, and then I'm going to write it to the I'm going to write it wirelessly via my NRF transceiver, which is set up as a transmitter. So I'm going to call the radio.write function, passing in the command. And again, the write function expects a C-style string. So I have to go command, which is a string variable, and I need to go .cstring. I need to convert it to a C-style string. Alternatively, I could have just, wrote this differently, so I just had a C-style string, but this is how I've done this. So command.c-style string. Now I'm writing the C-style string via write function, and I need to tell it the length, the number of bits I mean to write. The same when we read it, we had to tell it the length. So command.length, so I'm writing this command, and it's at this length, and I'm writing the function. And kind of a side effect of the write function is, normally before when I wrote this in previous videos and stuff, we just wrote it. Right now I'm encapsulating it in an if statement, because a side effect is that the write function returns a Boolean. True if it successfully was able to transmit the data you wanted to transmit, and false if it wasn't. So if this is true, meaning if the data actually successfully got transmitted, I'm going to just output that to the serial monitor saying, hey, command sent, and whatever the command was. Else, it returned false, meaning the command wasn't sent. I'm just going to be like failed to send. So those are the quick little bit of functions. So you can see already a lot less code to the transmitter. Just setting up that radio and creating a couple functions for handling, setting up the radio and then handling the serial input, because I'm going to be typing something in. And then my setup function is really simple. It sets up the serial monitor again at this higher baud rate, where where it's high enough to be really quick, but low enough that it's not going to cause too many problems. Again, you could just put this at 9600, as long as you have your other code set up as 9600 too. Make sure they have the same baud rate. And then again, I'm just going to wait for the serial monitor to set up. As soon as that sets up, I'm going to initialize the radio. And I pass in the argument TX. Remember, in this one I have to pass in an argument because I didn't include a default argument. Plus, even if I did, it would have been defaulted to RX, and I need this as a transmitter. So I initialize the radio. Very simple setup. Sets up my serial monitor communication and waits for it to set up, and then sets up my radio. And then the loop is even simpler. The only thing I'm doing in the loop is constantly handling serial input. I'm just continuously checking to see if the user has typed anything into the keyboard, because then I'm going to wirelessly transmit that. So just see the difference in code here. This is the entire, I'm just going to zoom out so you can kind of see. This, I'm going to zoom out a little more. But this is the entire transmitter code. From here to here, not much. So yeah, so that's all the code. So again, back, that's all the code. So yeah, without further ado, I say we get to, now that we've talked about the code, we'll get to a live demo. So I'll shut things down and I'll hook up a live demo and we'll be back.